Hello everybody, this is Dr. Christopher White, and in this presentation we're going to be looking at the 4 different types of rocks. This is going to correspond to section 1.5 in your textbook. So when we think about rocks, we see that they fall into 4 distinct groups. There are sedimentary rocks, igneous rocks, metamorphic rocks, and hydrothermal rocks. And so we're going to go through these 4 groups and we're going to look at how we separate them from one another. So we're going to start by looking at sedimentary rocks. Now, sedimentary rocks form on the Earth's surface only. And so this means that sedimentary rocks form on the continents or they form in the oceans. So just to be clear, the ocean floor is still counted as the surface of the Earth. Now, the thing that we see with sedimentary rocks and what makes them so helpful to geologists is that different environments produce distinctly different rocks. So if we look at this picture here, what can we see? Well, we can see we've got a continent here and an ocean here, and the great thing is that several of these different environments are going to produce very, very distinctive and different sedimentary rocks. So if we look at this picture here, you can see we have a glacier, we have a river, we have a lake, we have mountainous terrain over here, we have a desert area here, we have a beach here, and we have an offshore ocean environment here. And each of these different environments are going to form distinct rocks because the processes that operate in them are different. So the way the sediment is being moved around will vary between environments. So for instance, over here in the glacial environment, obviously the sediment is being moved around by solid ice in the form of a glacier. In the case of the river, the sediment is being moved by liquid water. In the case of the mountainous environment, the sediment is being moved by gravity. And in the case of the desert environment, the sediment is being moved by the wind. In the case of the beach environment, the sediment is being moved by waves. And in the case of the offshore environment, the sediment is going to be moved by a mixture of waves and tidal currents. And so each of these differences in how the sediment is being moved is going to affect the types of sedimentary rock that form in those environments, and it's also going to affect some of the structures that form as the sediment is moved around, and these structures can sometimes be preserved in the sedimentary rocks. And so the sedimentary rocks are the result of a sediment being formed, it is transported, and then it's deposited, and then the sediment gets squished, and it essentially gets turned into a rock through the process of lithification. So sedimentary rocks are rocks that form in normal surface environments, and they consist of a few different types, but the 2 most important ones are the clastic sedimentary rocks. These are sedimentary rocks that consist of sediments which contain clasts. And a clast essentially is a piece of rock or mineral. So just think of a beach sand. Okay, you go to the beach, you put your hand in the sand, and you can feel each of the little sand particles as you rub your fingers together. Each one of those little particles is a clast. Now, obviously, if you take that sediment and you squish it hard enough, you compact it, you can make the sediment stick together and form a solid rock. That's lithification. Now, the other class of sedimentary rocks which are out there are the carbonates. And carbonates tend to be formed due to accumulations of calcium carbonate. And this is going to lead to the formation of a rock which we refer to as a limestone. Now, a lot of limestones form in environments where we have a build-up of large amounts of shells. So that could be bits of coral, bits of oyster, bits of, just sea life in general. Okay, so think of an environment like a reef or a lagoon. In those environments, you can build up big, thick sequences where you get loads and loads of animals living. Obviously, lots of them die, and so their shells get incorporated into the sediment in that area. And once again, if you take that layer of sediment that contains all those shells and you compress it and you squish it really, really hard, you increase the temperature, you can make all that calcium carbonate in the shells essentially form a limestone. And so sedimentary rocks on the whole consist of a couple of broad groups: the clastic sedimentary rocks and the carbonates. There are lesser groups of sedimentary rocks, but we're not going to discuss those right now. So if we look at this picture here, we can see a sediment that's forming in a steep mountain front environment. So what can we see when we look at this sediment? Well, obviously we can see the solid rock up here, which is eroding. So that's the sediment source, and we can see the sediment which is forming from the erosion of this layer of rock. So what can we see? Well, we can see that these pieces of rock are very, very large, and we can see they're very, very angular. They've got lots of sharp corners. We can also see that there is a very, very big range of class sizes. So you have everything going from big meter-sized pieces of rock here, probably all the way down to little fragments of rock that are going to be the size of a clay, which is super, super fine. So what we have here is we have a very poorly sorted rock that has clasts which are very, very angular. And as a geologist, this is very helpful to us. So if we come across a layer of rock that is made up of big angular clasts like this, and the rock is very poorly sorted, so it has a very big range of clast sizes going from really, really big clasts to really, really small clasts, well, as a geologist, we can compare that to the modern environment, and we can say, right, I think this layer of rock, or should I say the sediment that went to form this layer of rock, was deposited in a steep mountain front environment. And this comparison of modern environments to rocks is very, very important, because it actually has its own special name. It's called the principle of uniformitarianism. And the principle simply states, if it's happening now, it's happened in the past. And so we can look at modern sediments that form in steep mountain terrains, and we can use the evidence we collect from those, and we can compare it to rocks which we see in the rock record, and that allows us to work out the environment in which that sedimentary rock formed. So let's think about another environment. Here we have sand dunes. Now, sand dunes, as I'm sure you know, tend to form in desert environments. Now, the question obviously becomes, well, hold on a second, why do we have an environment where we have lots and lots of sand building up? Well, deserts and sand dunes tend to form in environments where there's relatively little water. And so this means the sediment isn't being moved around by water, it's instead being moved around by the wind. The wind is blowing the sediment. Wind is typically not that strong, so it can't blow really, really large clasts of rock. It can't move them, they're just too heavy. So the wind tries to move them, it can't do it, so it leaves them behind. In contrast, the really, really light pieces of rock, the really small ones, are so small and so light that they can be picked up by the wind and they can get blown out of the area, huge distances away. And so this means that the wind can only move a very, very limited size of clast. It can't move the really, really big ones, and the really, really small ones get blown away by the wind and they're lost. So the only size of clast that the wind can start to move are clasts which we refer to as sand-sized. And so this means that these sand-sized clasts get blown about by the wind and they start to form these large structures which we refer to as dunes. And so this is why these very dry desert environments tend to be dominated by sands, because that's the only class size that the wind can easily move. And of course, as the sand builds up, it will tend to pile up and it will form these very, very distinctive dune structures. And once again, if we go on the rock record and we start to look at a sedimentary rock and we see that it consists of lots and lots of sand, that sand is very well sorted. And if we look in the rock record, we can see signs of dunes having been in the area as well. We can say, right, there's a good chance that this rock will have formed in a desert environment. So once again, we're taking the modern environment and we're applying what we see in the modern environment to the rock record. And that's allowing us to work out the environment of deposition for that particular sediment that went to form a rock. So let's look at this final environment here. Here we have a beach environment. So the first thing you'll notice is this isn't a sandy beach. This is a pebbly beach. So these are pebbles. Okay. Now, this instantly tells us something. This means this beach is probably quite a high energy beach. When the waves hit the beach, any sand-sized class, any small material, gets pulled back out to sea as the wave retreats. Because remember, the wave comes from the ocean, it hits the beach, it goes up the beach, and then it comes back down the beach. And if there's any light material mixed in the sediment, the light material gets picked up by the water and it gets pulled out into the deeper water, into the ocean. And that means what's left behind are the class that the waves can't move very, very easily. Now, normally waves aren't too strong, so they can't move, particularly large material. So that means they leave behind material that, like sand, for instance. That's what most beaches are made from. In this particular instance, though, we have a beach where clearly the waves are more powerful, and so even the sandy material is getting pulled out into deeper water and it's gone. And only the coarser material is getting left behind in the form of pebbles and cobbles. So straight away, this is telling us that this is a high energy environment. Now, you're thinking to yourself, well, hold on a second. How do we know that this sediment didn't form in a mountain front? I mean, both this sediment here and this sediment here both contain large pieces of rock. But there's a couple of things that a geologist can look for which will help us work out the environment in which the sediment was deposited. The first thing you'll notice is that these clasts are quite well rounded. They don't have lots of sharp corners. Compare that to these clasts here, where you can see they have lots of sharp corners. So that's an indicator straight away that we're looking at a different environment. Typically, the rounder the clast, the longer it's being transported for, because as the clast gets transported and moved along, the sharp corners get knocked off. And so this tells us that this clast here, for instance, has been transported enough to knock off all the sharp corners. In contrast, these clasts here, which formed up there, have only been transported a few hundred meters. So they haven't had time to have the sharp corners knocked off yet. Another thing that will allow us to work out the environment in which the sediment is being deposited is the fact that mixed in with all these cobbles and pebbles, there are going to be pieces of shell. There are going to be shell fragments mixed in there. And obviously a good paleontologist, so a geologist that looks at fossils, can come along and they can look at the bits of shell and they can work out that this is the shell that comes from a marine organism, the type of organism that lives in a beach environment or in the oceans. And so straight away that's going to tell us that the sediment we're looking at is formed in a beach environment. Now in the case of this beach environment, what's moving the sediment around? What's doing the transporting? Well, it's the water, it's the oceans, or more accurately, it's the waves. So as the wave hits the beach, it pushes sediment up the beach, and as the wave retreats, it pulls sediment back down the beach. And so it's constantly moving the sediment backwards and forwards and backwards and forwards. And so, once again, as a geologist, what we can do is we can look at modern environments like this picture, and we can take the data that we collect from the modern environments and we can compare it to the sedimentary rocks that we see in the rock record. And that will allow us to work out the environment of deposition in which the sediment that went to form the rock was deposited. And so, once again, that's the principle of uniformitarianism. And this is why sedimentary rocks are so helpful to geologists, because they tell us what was going on the surface of the Earth. The other three types of rock, igneous rocks, metamorphic rocks, and hydrothermal rocks, are typically helpful for telling us what's going on inside the Earth. So sedimentary rocks have a very, very unique position, and they have and they're extremely helpful for geologists when we're thinking about what's happening on the Earth's surface during geologic time. Okay, so now let's move on to igneous rocks. So igneous rocks are rocks which form from the cooling and solidification of magma. So magma, for want of a better way of describing it, is just liquid rock. So if you take a rock, you melt it to form a liquid, that liquid is magma. And magma is naturally very, very hot. So that means it's very, very buoyant. So it wants to rise. And so when you form magma deep in the earth, because it's hot and buoyant, it wants to start rising towards the earth's surface. And it will try to do that. Now, to be clear, only a very, very small amount of the magma that forms inside the Earth ever makes it to the Earth's surface. About 90% of the magma that forms inside the Earth never makes it to the Earth's surface. And so this magma gets trapped inside the crust, where it slowly cools down and it solidifies to give us what's referred to as a plutonic igneous rock. So these are igneous rocks that form underground. The magma cools slowly. And so that tends to give us igneous rocks that have big crystals. Because the magma cools slowly, it means the crystals can grow very, very large. Now, the remaining 10% of the magma can make it to the Earth's surface, where it will be erupted via volcanoes. Now, when the magma is erupted onto the surface of the Earth, it's given a different name. It's referred to as lava. Now, lava, when it's erupted onto the surface of the Earth, will cool very, very quickly. And so this will give us igneous rocks with very, very small crystals. So you're thinking, well, hold on a second, why does it, cool so quickly? What you have to remember is that this magma, this lava, is going to be at a temperature anywhere between about, 900 Celsius and 750 Celsius. So it's very, very hot. And it's going to come in contact with the air, which is about, let's say, 20 Celsius. And so that's a very, very big difference in temperature. And so it's literally, for the lava, it's going to be similar to you jumping into a pool full of ice water. You're going to get a shock. You're going to cool down very, very quickly. The same thing happens to the lava. It's going to lose, its temperature very, very fast, and it's going to solidify and form a, volcanic rock. Now, the other type of volcanic rock that can form are rocks which are related to explosions. So sometimes when your volcano erupts, it produces a lava flow, but sometimes when it erupts, it goes boom and it blows up. And this produces a lot of ash as part of that explosion. And the ash will go up into the atmosphere, and then gravity will kick in and it will get pulled back down onto the Earth's surface. And this ash will essentially fall on the side of the volcano, and it will form a type of rock which we refer to as a pyroclastic rock. So in terms of magma that makes it to the surface of the Earth, it forms a class of rock which we refer to as volcanic rocks. And there are two groups of volcanic rocks. There are volcanic rocks which are related to lava flows, and there are volcanic rocks which are related to pyroclastic material, the explosive part of the eruption. In all instances, though, be it the plutonic rock down here inside the Earth, the volcanic rock produced by the lava flow, or the pyroclastic rock produced by the explosion, in all of those three situations, the rocks which are forming are the result of cooling of magma. So when your magma cools, it gives you an igneous rock. So here we can quite clearly see this is an explosive volcanic eruption. You can see all the ash and dust created by the explosion, and you can actually see some of it coming down the sides of the volcano here and here in the form of what are referred to as pyroclastic flows. And these are very, very dangerous because they're full of superheated gas and ash and dust, and they move very, very quickly. Typically, anywhere in up to a couple of 100 miles an hour. So if you're familiar with your classics, you may have heard of the city of Pompeii in Italy. That was on the flanks of Mount Vesuvius, and when Mount Vesuvius erupted, it produced a pyroclastic flow like this that went straight into the city of Pompeii and essentially buried everyone in this superheated ash and dust, killing everyone instantly and essentially preserving the city almost perfectly. And then, of course, we have volcanic rocks which are related to the cooling of lava flows. So you can see in this case the lava is being erupted, and you can see here it's pouring out onto the surface and it's slowly solidifying, and it's going from the red hot lava here and it's cooling down to form the black rock which we can see in the foreground. Now in both of these cases, these are examples of volcanic igneous rocks because they're forming on the surface of the Earth due to processes associated with volcanoes. So the third type of rock which forms are metamorphic rocks. Now metamorphic rocks are the result of changes in temperature and pressure. So I can take a sedimentary rock, I can take an igneous rock, or I can take a hydrothermal rock, and if I put it under enough pressure and temperature, I can actually make the minerals in that rock change into new minerals. So the thing is every mineral has a certain pressure and temperature range in which it is happy. As soon as you increase the temperature too much or increase the pressure too much, the mineral becomes unstable and it has to change into a new mineral which is stable at the new temperature and pressure. And this process of taking the first mineral, changing the temperature and pressure, and making it change into a new mineral is referred to as metamorphism. And so metamorphism can only occur in areas where we have quite high temperatures and quite high pressures. So a good example of a place where we can get metamorphism is actually along the margins of areas where we have magma entering the crust. So the rock here isn't being melted by the magma, but the heat from the magma is going to affect the rock, and it's because it's being heated up, it's going to make the minerals change, so it's going to metamorphose it. Over here we have a situation where our rock is being compressed really, really hard. Once again, the increase in pressure is also going to make some minerals unstable, and so they're going to have to turn into new minerals. Now, another thing that happens during the formation of metamorphic rocks is because a lot of the metamorphic rocks are associated with quite high pressures, it actually controls the direction in which the minerals form. And so this can lead to the formation of rocks like this gneiss here. And you'll notice it has this very, very distinct banding. You have these light and dark bands, and you can also see how tightly folded it is. And this is the result of the pressure, the fact the rock is being squished so hard. It's making the minerals split up into these light and dark layers, and the fact the rock is being compressed is causing these layers to become folded in this very convoluted and complex fashion. And so this is showing us, one of the textures which we tend to get in these metamorphic rocks. On a lot of occasions, we tend to see metamorphic rocks that have this very, very distinct layering to them, which is the result of the pressure. Now, the other thing is with metamorphic rocks is because they're the result of increasing temperature and pressure, they tend to form very, very distinct minerals. And so metamorphic rocks tend to have very, very distinct textures, and they tend to have very, very distinct minerals in them. And so that's how geologists can recognize them versus the other types of rock. Now, the final type of rock are the hydrothermal rocks, and these are formed from minerals which precipitate from hot water. So what you have to remember is that although it doesn't look like it, the Earth's crust is absolutely stuffed with water. There's loads of it in there. And as that water gets heated up, it naturally starts to circulate. And as the water circulates through the rock, it does what we call scavenge. So as the water circulates around through the rock, it will steal elements from the rock that it's passing through. So it might steal some copper or some silicon or some cobalt or some nickel, whatever it feels like. If it can steal it, it will. So as the water circulates around, it scavenges these elements. It pulls these elements into solution. It dissolves them into the water. Now, as your water circulates around, remember, underground it's nice and hot. When the water exits onto the surface of the Earth, or when it at least approaches the surface of the Earth, the temperature starts to drop very, very quickly. And so as the temperature starts to drop, well, that means that the ability of the water to transport the stuff that it's dissolved in it decreases. So when the water's hot, it can dissolve loads and loads of stuff. However, as soon as the water starts to cool down, it can't keep all of that stuff dissolved in the water. So it has to start getting rid of some of it. And it gets rid of some of it by precipitating out minerals. It takes the stuff that's dissolved in the water and it turns it into a solid mineral. And these rocks, which are formed by these minerals being released by the cooling water, are hydrothermal rocks. And so if we look at this picture here, you can see here we have a geyser, and you can see here's the hydrothermal water here. So this is very, very hot water. It's going to be absolutely stuffed with loads of stuff which is dissolved in it. And you can see though, as the water's cooling down, it's depositing the minerals. You can see that here in the form of these rusty minerals here and these white minerals here along the edge. And so these are hydrothermal deposits. Okay, everybody, so that's it for this presentation. So as I said, that corresponds to section 1.5 of your textbook. Please take some time and really read that section well, because it's going to help you later in the course when we start discussing these rocks in greater detail. All right, thank you for your time.